Write one GPU kernel, run it on NVIDIA, move it to AMD, then try it on Apple Silicon without rewriting the entire algorithm in a different language. That is the bet behind Mojo. Not Python is dead, not CUDA disappears tomorrow, and not the unsupported claim that one Vulkan switch makes every accelerator identical. The real question is whether a shared language and compiler stack can make GPU code less dependent on one vendor without giving up the control that high performance requires. To understand the opportunity, start with CUDA's moat. CUDA is more than a programming syntax. It is a mature stack of compilers, libraries, profilers, optimized kernels, documentation, examples, and developer knowledge. A company may buy NVIDIA hardware because the software works. Then it writes more CUDA-specific code, which makes the next NVIDIA purchase easier. Hardware adoption strengthens software adoption, and software adoption strengthens hardware demand. Escaping that loop is not as simple as translating one file. GPU programs care about threads, blocks, grids, warps, memory movement, synchronization, occupancy, and hardware-specific operations. A portable layer must expose enough control for performance while hiding enough vendor difference to make reuse worthwhile. Mojo attacks that layer as a systems programming language for CPUs and GPUs. Its current manual includes low-level GPU primitives, device contexts, kernel functions, grid and block dimensions, memory operations, barriers, and synchronization. This is not a decorative Python wrapper around a remote service. The developer is programming the execution model. The syntax is designed to feel familiar to Python developers, but the performance path comes from static types, compile time parameters, ownership, and explicit control. Imagine a vector addition kernel. The host allocates input and output memory. Data moves to the device where required. A device context compiles and enqueues the kernel. Threads receive indices inside a grid. Each thread handles its element. Then the host synchronizes and reads the result. The important promise is that the same high-level Mojo source can target compatible GPU backends while the compiler lowers the program toward the selected hardware. Official Mojo material now discusses NVIDIA, AMD, and Apple GPU behavior. AMD support was a highlighted milestone in the 25.4 release. Current GPU tutorials include NVIDIA examples, AMD distinctions, and an Apple Silicon limitation around printing inside kernels. That is stronger evidence than a future roadmap slide. Real documentation has to explain where platforms behave differently. But portability is not sameness. NVIDIA warps, AMD wavefronts, Apple GPU architecture, memory hierarchies, supported data types, and vendor libraries differ. One source file can still require tuning branches, hardware-aware parameters, or different optimized kernels. A compiler can share structure without making physical hardware identical. This gives Mojo 3 practical entry points. The first is kernel authorship. If your team writes custom math, image, simulation, or AI kernels and wants one language spanning CPU and multiple GPU targets, Mojo is directly relevant. The second is the Python hotspot. Keep the Python application, identify one expensive operation, implement that operation in Mojo, and call it from Python. You do not need to rewrite the product to test the value. The third is framework infrastructure. Modular's repository includes an open standard library, GPU and CPU kernels, model pipelines, examples, and inference components. A team can inspect and extend parts of the stack instead of treating every kernel as a black box. Now the honesty section. Mojo is still young. Current documentation identifies beta versions and active evolution. APIs can move. Libraries, debugging knowledge, package availability, and community answers are much smaller than CUDA's 20-year ecosystem. Open also needs precise language. Modular has released a large amount of repository code, including the standard library and many kernels. The repository uses an Apache license, with levying exceptions for its contributions, while broader Modular Max and Mojo usage is also governed by a modular community license. The official site has continued discussing the path toward greater openness. So open source is not one switch covering every compiler, binary, service, and usage right. Check the exact component and license you plan to ship. There is also a new dependency problem. Moving away from NVIDIA-specific code can reduce one form of lock-in while increasing dependence on a younger compiler platform. The correct question is not, is there a vendor? The correct question is whether the interface is portable, inspectable, maintainable, and supported if the vendor changes direction. Here is the adoption test. Choose one real hotspot, not an entire application. Implement the smallest representative kernel. Run it on every target you claim to support. Measure correctness first. Then measure compile time, startup, throughput, memory use, and the engineering effort required for tuning. Compare against the best practical baseline, not slow pure Python. If production uses NumPy, PyTorch, CUDA libraries, or vendor-tuned kernels, That is the opponent. Test numerical behavior as well as speed. Different targets and fast math choices can change precision, ordering, and reproducibility. A kernel that is portable enough to compile but produces unacceptable error on one backend has not met the product requirement. Record tolerances, representative inputs, and hardware-specific exceptions beside the benchmark so every claimed target passes the same acceptance test. Finally, test maintenance. Can another engineer understand the code? Can continuous integration build each target? Can a profiler explain the bottleneck? What happens when the compiler version changes? Adopt Mojo now. If cross-vendor GPU kernels are a strategic requirement, your team can tolerate a young toolchain, and one painful hotspot justifies the experiment. Watch and wait. If mature libraries, stable long-term interfaces, regulated toolchains, or maximum NVIDIA-specific performance dominate your work. Stay with CUDA when the product is all in on NVIDIA and the last percentage of tuned performance matters more than portability. Use Mojo beside Python when one expensive operation is the problem, and a complete rewrite would be irrational. Mojo's strongest idea is not that every chip becomes the same. It is that developers might keep one programming model while the compiler and kernel stack absorb more of the difference. CUDA's moat is real because the ecosystem is real. Mojo's opportunity is real because hardware diversity is increasing. The winner will not be decided by one benchmark headline. It will be decided when teams can write, profile, ship, and maintain the same serious workload across the hardware they actually own. That makes the trade-off worth testing.